Okay. All right. So the topics of today's lecture are is or are entropy and error correcting codes. I think relatively light lecture, but we'll see. All right. Whatever. We've done a lot of stuff before. Last couple of classes with a lot of stuff using the additive Chernoff bound, and I think that's actually going to be the case again today. So that included the geometric stuff, epsilon samples and epsilon nets, and then all this learning theory stuff. It seemed like we're using the additive Chernoff bound always as opposed to the multiplicative. So today, which is actually lecture 14, can you believe it? I can't. Today is about error correcting codes, just an introductory lecture on error correcting codes and some connections to randomization, as well as connections to this mysterious thing called entropy. So, okay, entropy and error correcting codes. All right, so what's the model? Okay, so you have two people, I guess at point A and point B, and person at point A wants to say something to point B. Okay, so they want to send something. And what makes this interesting is that we're going to assume that as person A yells at person B, some of the bits get screwed up in transmission. So person B might receive a slightly different message. Sorry. Oh, let me do something. So the person at point B may get a slightly different message. Okay, and the exact model we're going to study is where there's some fixed probability P, and every bit may get flipped independently with that probability. Okay, and so the question is, how can person A reliably communicate to person B? Right, very basic problem. Very important problem, especially like 1920s, 30s when phones are new and stuff like that, and telegrams are new or whatever they used. Okay, so not all of these things have been worked out at that point in time. Okay, so let's say, well, you guys have probably dealt with this before. I assume many of you are from overseas. I get the impression. I am too. So you talk to your parents overseas, and if you're using an old phone, then maybe they can't hear you so well through the phone. Or actually, it doesn't have to be overseas. Maybe your parents are just so old they can't hear you so well. Okay, so you say like hello, and then they go what, right? And so okay, so what do? Okay, you say hello, they didn't understand. What would you say? You just say it again, right? At least that's what I do. You just say the same thing over and over again until you get through one sentence. Okay, and good, one sentence down, and you repeat. Okay, so that is arguably an error correcting code, right? At some level, I want to communicate something, so I repeat it over and over again until the person on the other end starts to notice there's some resemblance between the thing that's repeated over and over again, and they put something together that's coherent. It's not so different than my teaching philosophy. Okay. All right. So I guess a slightly to broaden this a little bit. Uh, so the high level idea is maybe there's some kind of code. Okay. So I have my original message X, and of course something very boring is to repeat it 10 times and send it over. But maybe you can be more clever and more efficient about your redundancy. Okay. I mean, obviously the cost of repeating 10 times is that you have to repeat it 10 times. It would be great if you didn't have to multiply the length of your message by so much. So the general framework kind of assumes some kind of encoder. So you start with, say, an M bit string. M is going to be the smaller number, and you're going to encode it into a longer string n. If you're repeating 10 times, it'll be 10, n equals 10m. Okay, and then the longer string will get sent over to wire. The longer string will get flipped. Okay, but you're hoping that your longer string has some redundancy or some kind of safety mechanism built in, so that there could be some kind of decoding function that takes your longer string and extracts the shorter one. Okay, so in the case of just repeating over and over again, if I wanted to repeat 10 times, then maybe the encoder C of x would just like concatenate x like let's say 5 times or something. Okay. All right. Okay, so that's fine. Now the decoder will, at some level, take in those 5 copies of x, except some bits may get flipped. Okay, so I'll write it as I'll write x1 prime, x2 prime, x3 prime, x4 prime, x5 prime. Okay, so in our model, we're assuming that you save all the bits. You just still send n to n to keep it simpler. Okay, so what I'm saying is that x1 prime maybe refers to the first x getting garbled, x2 prime, the second x being garbled. Okay, so, all right, so how might you define the decoder? Okay, so in other words, you're taking in this longer message and you want to output now one thing of m bits. Like what might be the first bit be, second bit be, stuff like that. Okay, so we can take the average. So I guess the ith bit is the average of, it would be, I guess, x1 prime. I'll write that to be the ith bit. Something like that. Okay, so if this was like I should have wrote them all out. If this was like a 1 and a 0, and then there's maybe a 1 and a 1 and a 0, what would the average be? Sorry? 3/5 or something? Okay, so we failed to output a bit. All right, so let's come up with a coding scheme where we actually output bits. Yeah, majority. Majority is fine. And I guess it'll also correspond to the median, which is probably what you meant when you said average. Okay, so if we did the majority, then we would output 1. Okay, so in other words, to screw up a message, you'd have to flip 3 out of 5 bits, and you're hoping that's less likely than just flipping 1. Okay, fine, so that's very simple. All right, did I obscure anything? No. All right, so let me just set up some notation then. So as we said, we have the part where you take the message and you put it into the code. We call that the encoder. And we have the part that takes the longer message and extracts out the original one, ideally. That's called the decoder. And we're going to, just to model the noise, so I'm going to be using this script n to be this kind of randomized function that flips every bit independently with probability p, just notationally. Okay. All right. And is there anything else? Okay. So if I wanted to pretend I'm smart by writing everything mathematically, what we want to show is that if you take x, we have to work our way out from inside out. You encode it with C, and you apply some noise with N, and you decode it with D, you get back X. That would be a successful transmission of the message. Okay, um, so in general, we're going to be adding redundancy, and our coded um, the coded words will be longer than the input words. The codes will in general be longer. So n should be bigger than m. Uh, we're interested in the issue of how much bigger n needs to be. So if I were to kind of draw a diagram, I want to think of n as being the code side being much bigger. Okay. And as far as the mapping goes, a particular code word here, c of x is going to give it exactly one point over here. Okay. But in the opposite direction, there may be many points over here that get decoded to the same point here. Right? So for a majority, anything where the majority at least agrees will get decoded back. Okay, so there's a one-to-many kind of thing, or many-to-one kind of thing going on. Okay. We're not going to worry too much about whether the codes are efficient, whether there's, we just actually today we're only worried about basically making the list. Every point here needs to map over here. Every point here needs to map over here. I'm not worried about it being compact or anything like that. All right. Okay, so that's some notation. All right, so now, okay, so when I'm making a code system, I want to consider two things. What might those two things be? What am I looking for in a good code? Yeah. Okay, so of course we want to code successfully, right? We don't want errors. So the metric we'll use today will be the average error rate. Okay. So I'm really taking the average over all input words. Okay. So this is the odds of failing to decode X. So the probability is over A, choosing one input message randomly, and then also applying the noise in the middle. Okay, so this is the average over all input words, as opposed to saying every input word has to have this error. This is saying the average error over all inputs. Uh, a homework problem is about the stronger guarantee. Okay, so that's one consideration. And what's the second? Yeah. Yeah. So this is called the transmission rate. Okay, so right. Okay, so M is the number of bits on the input. N is the number of bits on the code side. So at some level, if this is like 1/2, it's saying I have to basically make 2 bits to send over 1 bit. Okay, so I want this number to be as close as 1 as possible. Okay. All right, so that's roughly the kind of efficiency of sending things over the wire. Okay, any questions? Just enthusiastic yawns. Okay. All right, so yeah, so last class somebody remarked about how we were doing results from the 80s. Well, here's a result from 1948 then. And this is a really big deal. So this is one of the several things Shannon did that was like a really big deal. Um, so he was working at Bell Labs and thinking about this problem. I think it's important to point out that he was also modeling the problem. Okay, so people weren't thinking about it so clearly quite like this at the point. So that's also something this paper does. So it kind of sets up the framework, sets up the model, everything we just went through. But so not only did he the goal is to find good codes because that's very useful to AT&T, of course. But he showed that in fact, he kind of pinned it all the way down to, and showed that the optimal transmission rate is 1 minus the entropy of P. So I haven't defined entropy yet. Mathematically, it's p log 1 over p plus 1 minus p log of 1 over 1 minus p. I have a slide about entropy coming up, but that's what it is. Okay. It corresponds to the entropy of a coin that flips heads is probability p. Okay. So what's remarkable is that the remarkable part is the word optimal. Okay, so as I'll explain with more details in a second, he's going to show you can get this transmission rate, okay, for like any fixed error. You can get this transmission rate, and you can't do better. So he showed both sides, right? And at some level, he took something that was sort of like a very practical engineering problem and turned it down to a science, right? He got this universal limit for something that was just this practical problem of talking to grandparents overseas. Okay? So it's quite something. It starts sort of a whole field, okay? Because I mean, we'll go over one code today, but then there's other reasons why you might want to develop codes further and stuff like that. But it all kind of starts here. Okay. All right. So let me give the fully quantified version of his theorems. So the first one, rats, I always do that, is the following. All right, so fix an average error delta. Okay. He says that for any fixed delta, think of delta as being pretty small, as small as you want to take it. There is a coding scheme whose transmission rate at least 1 minus the entropy of p minus delta, and error at most delta. Okay, so that's this is yeah. I'll just show it. It's your rate of kind of how many bits on the code side per input side. So it's between 0 and 1. 1 is like perfectly efficient. 1/2 means 2 to 1 ratio. 1/3 is 3 to 1 ratio. Okay, so all right, so you can do a little bit better than 1 minus entropy. Okay, and then the negative side states that for all delta greater than 0, any coding scheme with transmission rate at least 1 minus entropy of p plus delta must have average error at least delta. People look upset, so maybe I wrote something wrong. I should warn that my lecture notes on this topic is currently full of typos. So any coding scheme that's really much more efficient than 1 minus h over p actually can't have very good error rate. Okay, so in this framework, we're kind of thinking of delta as being something that's really going down to 0 and kind of being diminished relative to h of p. P is sort of fixed, and delta will imagine it being much smaller than h of p. Okay, and that sort of pinpoints 1 minus h of p as being roughly the right optimal transmission rate. Okay, and again, just to remind us, this is walking into a space that didn't have a lot of theory and stuff yet. All right, so let me briefly explain entropy, and then I'm going to introduce one useful property about it that's going to show up in the proof. And then whatever time remains of class, we'll just talk as much about entropy and do as many proofs as we can. But we'll try to get the coding stuff done first, and then otherwise I'll throw you to the notes to do some of that calculus. All right, so entropy, I'm going to define it for discrete random variables, so and finite actually. So let x be a finite discrete random variable, taking one of 20 values, 100 values, whatever. Okay, so here's how I define it. It's a little bit, I mean, it's the same definition, but the way I explain it is a little different. So we'll start with this. Okay, so let's say you have some variable x. Think of x as like, I don't know, like a loaded dice or something, so it's uneven just to make it interesting. Okay? And then you roll the dice and you get some outcome. And depending on the outcome, you're either like very surprised or you're not, right? So if you might be very surprised if the probability is very low, and you're not very surprised if the probability is very high. Okay. So let me define the shock to be the random variable where I roll that dice, and if it is something that should have happened 1 out of 10 times, it counts as 10 points. If it's something that should have happened 1 out of 100 times, it counts as 100 times. So sort of measuring how surprised or shocked I am by the outcome. Okay. Now, the entropy is, in some sense, defined as, if I roll this dice, how many bits do I need to describe my surprise? So the entropy will be the expected value of the log of the shock of x. Okay. So if I expanded out the definition of expected value, this would be something like summing over all possible values little x, the probability that x is equal to little x times log of the probability, 1 over the probability that x is equal to little x. Okay, so it's expected log of the surprise or shock or whatever. Okay, sort of an odd definition. I feel like at some level, you might not even be convinced it's a particularly useful definition if it weren't for the way that it shows up in so many fundamental applications, including today, error correcting codes. Okay. Actually, there turns out to be many nice properties about this. Okay, so that's the definition. So, for example, if you had a coin that flips heads with probability p, you would get p times log 1 over p plus 1 minus p, 1 over log of 1 over 1 minus p. Okay. And now this particular case where you're just doing a binary and variables probability p is quite common. So by convention, people just write h of p to refer to the entropy of this particular variable. Yeah.
So why is it like p? I've usually seen it as like p log p.
Sure. Well, the other way you may have also seen it is yeah, which is the same thing. This is also pretty common. I just don't know how to interpret it. This this shock notion is actually the best I can do as far as trying to give some kind of physical metaphor for it. Otherwise, it's just some formula that works awfully well. You can take that as well, right? So, okay. There's a famous, I can read it out loud now. There's this famous thing where, so Shannon at some point was a postdoc for von Neumann. Von Neumann's also a very impressive mathematician. And many years later, he was interviewed in a magazine about all this entropy stuff. And this is what Shannon said. He said, my greatest concern was what to call it. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. When I discussed it with John von Neumann, he had a better idea. Von Neumann told me, you should call it entropy, for 2 reasons. In the first place, your uncertainty function has been used in statistical mechanics, like physics, under that name, so it already has a name. In the second place, and more important, nobody knows what entropy really is, so in a debate, you will always have the advantage. All right. I think one thing kind of implicitly going on is I don't think logs were as commonplace in calculations either back then. And okay. All right. At least in math and engineering is there. All right. Here's the one fun fact that we're going to use about entropy. If you want to know how many subsets there are of n with at most pn elements. Okay, so I'm summing over I from 0 to pn and choose I. That's the number of subsets with at most Pn elements. It's at most 2 to the entropy of P times n. Okay? So for example, if you chose, uh, if S was a completely random subset of n elements, okay, uniformly at random where everything appears as probability 1/2, so that means you're going to choose just one of those sets uniformly at random, okay, then the probability that S has at most Pn elements is at most, well, there's that many possible sets that H can be out of this many, okay. So you get bounds like this, and this is actually fairly tight. Okay. All right, so we're going to take that as a fact now, and we'll see how much we can prove it at the end if there's some time permitting. But otherwise, we can just bottle this up and now let's talk about the impact of codes. Okay. All right, so we've got two sides to this theorem. Maybe the more fun one is to prove that there is a really good coding scheme. Okay. All right. Okay, so I left the picture up there just as an image, but I thought I'd give you guys a chance to think. So first, you can make M and N sufficiently large. Okay, so worry about sending large messages. All right. Any ideas for how to construct a good code? So majority is not going to be efficient enough. It's a hard question. Nobody solved this for a long time. Yeah, plus if I asked you what a Reed Solomon code is, we'd have the same problem. Yeah, there are other codes now by other names, that's true. But I'm just thinking of like kind of first principle ideas for fun. Okay, so if you want to do majority vote, then you're uh it doesn't necessarily have to be 1 over P, but you would want to take a majority of many things to be able to recover all the bits, right? Because you want to get the first bit and the second bit and the third bit. In fact, one thing about that first strategy we did is it's doing each of the bits independently. But it's quite possible that you could come up with ideas that somehow, right, like the redundancies. So in other words, your redundancy is just completely separated bit by bit. But it's not impossible that you can kind of mix the interactions among the bits, right? And that would allow for maybe something much more efficient instead of something that's kind of column-wise separated. But that's going to be the same thing, just rearranged, right? That's yeah.
So if every bit is flipped by probability, then I'm gonna expect that as an n things, I'm gonna get n p flips.
Yeah.
So I'm gonna add some bits that are gonna assume that I'm close to n p flips and disregard stuff that happened with really that would be really soft, let's say, with the previous. I would assume that I will never be really soft with
Okay. But I think the The description got a little vague when you said, I'm going to add some bits that.
Yes, generally it is not.
Okay, that reminds me of I had an advisor who had this great quote, which was, a prophet should never be too specific. Um, okay, well, it's a randomized class. Okay, so that's one hint. We're going to do something randomized. What's like the dumbest idea? Yeah. Okay, at some level, randomly flip bits. But you do need to ultimately. So C is actually a deterministic function, though. So C itself is a deterministic function that takes something and outputs something, and D is also deterministic. I guess it didn't have to be, but let's focus on deterministic. Randomly repeat this. Uh, well, what does that mean? Because like n has to be fixed, right? Our length has to be fixed, so that means probably the number. Yeah,
Randomly choose subsets and make really XOR those subsets.
that's more sophisticated than what I had in mind. But okay, that's some like I don't know. Take some subsets and see if you can get some math to add up or something.
So for next, this on the probability so see that the one has less probability we can allocate more root to it. We can just
Too complicated. Too way out of my range. Okay, so C needs to take some x for a particular x needs to assign some code word. Yeah.
I think there's saw this in analysis for specific correlation work is in the set of n-bit strings, we have basically what's valid code words and invalid code words, right? Because since we only have our input n bits, the encoder should only generate a subset of
Yes. Yeah.
unlawful words.
Yes.
And ideally, what we want is we want the valid code words to look very different from each other, so that it's very hard to.
Okay, so that's a reasonably good idea. So if I can map points to kind of things that are kind of well spread out from each other in terms of like many bits of far apart from each other, then that would be kind of good, right? Because that means the code words are very different. So many bits would have to be flipped for one to get confused with another. Okay, okay, fine. So that generates this idea of trying to choose code words that are very spread out. So I kind of red is much smaller, much smaller than because this is really 2 to the n, so it's like some power of 2 times bigger than red, right? So how can I assign red to blue so that the images are spread out? Hmm? Working too hard. It's also painful to do the dividing, I think. Too hard. It's randomized class. No hashing. But that's the well, kind of. But I mean, hash functions also usually emphasize like pairwise hash or whatever. No, that, even more crude.
I'm trying to say that the whole space could be divided in different locations. We can assign for each code word like a space for each specific, and the distance between these places should be enough to the collision.
Okay, so okay, but now I want to come up with a really lazy way to divide it and spread things out. I don't even know how. I imagine it'll be tough to do it manually. Yeah. Ah, okay. Here is whatever the glorious optimal coding scheme. Okay. So we're just going to completely random function. Every input word is going to choose a completely random output word independently. Okay. All right. So now, what would a decoder look like? So if I have yeah, how might I define a decoder? Let's see, do I give it? Yeah. Oh, I did give it. Okay. Did you already? Okay, so the natural way to decode a message then is that because you have some message garbled thing is to find the closest code word nearby, right? And then get the X that gives you that code word. So that will be our decoder. So again, this is not at all worrying about efficiency and stuff. So just imagine we just build a big list or something, or we just scan things. Okay. So we're going to analyze a completely random code. Okay. And the decoder is just going to do sort of the most natural thing, which is, so I should mention, so this is the L0 norm. This is a fancy way of saying, in general, A minus B, the zero norm, is the number of coordinates I where AI is not equal to BI. Okay, so just a shorthand for how many bits are different. Okay, so you're just going to find the point X that has whose code word has the fewest bits different. That seems very logical, right? So the real thing is to do the random code. Any questions? Okay. Did I leave any hints for me? Oh, I drew a picture. Okay. Bummer. Okay, so that means that for point X that gets mapped to C of X, there's some region around C of X where it's the closest point and it gets mapped back to X. Okay. Depending on how crowded these things get, some of the regions may be slightly smaller, slightly bigger than others. All right. Okay, so we want to prove that this gets this glorious transmission rate. Okay. So up there I said, okay, we're going to let n needs to be sufficiently large because we're going to do some things that require that, and m will be 1 minus hp minus delta. Now you need to show the error rate is that much delta. Yeah. Okay, so the transmission m divided by n will be that 1 minus hp minus delta that was claimed in the theorem. So that's established. Now we just have to worry about the average error rate being at most delta. Okay. So I should point something out, though. Well, let's see. At some level, mm, uh, uh, at some level, we're analyzing random code, but we haven't really. It's not clear that a code exists and stuff like that, right? Like, there's no kind of fixed code either. That nuance will make more sense later. Okay. Okay. To prove this thing, let's let epsilon be really small. Okay. Entropy, if you remember, was some function of p's and logs. Okay. And in particular, a very small change in p results in a very small change in entropy. I mean, it's a continuous function is all I'm saying. Okay. So we can always choose epsilon to be small enough so that if I increase p by a 1 plus epsilon factor, then the difference in entropy is at most delta over 2. Okay, however small that needs to be. It's some function of p and delta. I don't care. Okay. All right. So let's fix a particular point x. Okay. And we're going to make two claims. I want to analyze the probability of screwing up x. Okay. So my first claim is was probability at least 1 minus delta over 2. So nc of x is flipping bits in c of x, transmitting c of x. The number of bits flipped is at most 1 plus epsilon p times n. Okay, so that's one. The other one, okay, is that was probability at least 1 minus delta over 2. No other point x prime has its code word within 1 plus epsilon p of n bits. Okay. So those are the two claims. So one claim is that the code word for x will be close to the message. And the next claim is that no other code words will be close to the message. Okay. Now, when I say rand probability, there's two sources of randomness. Okay. One is from the noise, and the other is from the code itself. All right. So, okay. So we'll do the two claims separately, but first let's explore the consequences. Okay. Just want to make sure I don't screw it up. All right. So, all right, I want to show, okay. So now if I looked at this particular x and I said, okay, what is the probability that DC, no, I get this wrong, DNC, so the transmitted message is equal to x. How might I analyze this if those claims were true? Yeah, so maybe it's easier to not equal to x. Um, okay, so if oh no, I'll just do this. Okay, so it was, okay, so it was probability, okay, so it was combined probability 1 minus delta, because there's two probability errors of delta over 2 that add up to delta. We will have that x is the only point, c of x is the only point within 1 plus epsilon p of n. So, okay. Okay, so this thing is at least 1 minus delta. Okay, here I'm really still kind of treating c as a random word. Okay. All right, so what have we shown? Okay, so we've kind of shown that, okay, so let me put it this way. This is good. Okay. Now, okay, so this is a little subtle. So what we've shown is that for a fixed value of x, the probability that we don't decode the message, but it's a little bit different. It's saying that if I mapped everything to a random thing and then I applied noise and then I map back to the nearest code word, the odds of not getting it is delta. Okay. What we're interested in is showing that there exists a code with average error at most delta. Here we've kind of shown if you do this mathematical experiment where you choose all the C of x's randomly and you apply noise, then you'll probably get back the original message. There's a slight distinction there. Okay. All right, so in other words, I want to show, so let me be more clever. So even if I also randomly chose x, in other words, if I randomly chose x, I randomly chose c, and I randomly applied noise, this is what we've shown. Okay. What I want to show is there exists c that if I apply the probability over a random choice of x and random noise, sorry, the c looks like a parentheses, typical confusion. Okay, so I want to, in other words, I kind of want to take out the probability over c. Does that make sense? There's a distinction here. So what we directly analyze is if I chose c randomly, the probability that this kind of thing doesn't come out to be x is at most delta. But I want to show that there exists a fixed c, a fixed, concrete, no longer random c, such that if I now choose random x and I apply random noise, I get back. Okay, so how do I do this? Yeah. Yeah, so how are we going to, we want to do a probabilistic argument, a probabilistic method kind of argument. Okay, so how do we kind of articulate? So, in other words, you said something about an average, right? So what is the average, yeah, so let's expand that. So we have this kind of idea, oh, if you have some kind of average, something beats the average. But now we have to kind of fill in what those terms are to really clean up this argument, right? That is exactly the style of argument we want to make. So kind of what is the average of, and so it should be expected value of something, right, over something. Where's the randomness? Where's not the randomness? so to speak? What should I write down to sharpen this argument? Yeah.
we have chosen a C over all possible C's with a C probability
Yes.
rates.
Okay,
So
so
we can rewrite the above probability as the sum of choosing a specific C times the probability of this specific C being
okay, so maybe you're saying that I can this left-hand side is equal to the sum over all possible C's, I guess. Uh, for lack, this is of course going to make no sense notationally, but hopefully you guys understand what I'm saying. The probability that we choose C to be C, okay? Uh, the probability that D N C X is not equal to X, given we've chosen C to be C, right? So another way to write this um, is the expected value over C, the probability that D N C X is not equal to X, okay? Which I guess if you want to write it even more is the expected value over C, the average error rate of C. That was just how we define average error rate, okay? So if we kind of now worked from the bottom and got all the way back to the top, we've now shown that the average error rate over a random C is at most delta, okay? So if I, out of all random codes, the average error of the code, the average of the average error of the code is at most delta. That puts it in the form of something beats the average. Now there exists some C with code at most delta. Okay, so Shannon used an old trick where he didn't actually give him a code. He just showed there exists a code, wrote a paper, and walked away. He left that work to everyone else. And then that became a big field to actually pinpoint and be able to describe them. Okay, so there is a very nice probabilistic method proof. I feel like it's the most practical example I can think of, like real world example of using the probabilistic method to prove something. Okay. All right. So if the claims are true, then that actually shows that there exists a good code. All right. So now let's figure out these claims. Was probability at least 1 minus delta over 2, assuming n is sufficiently large, the expected number, the number of bits flipped is at most 1 plus epsilon pn. Why? Sorry? Oh, okay, multiple. So I can write this as no, I can write this as, oh no. I can write this as some sum of independent random variables. If the ith bit is flipped. Okay. So the expected sum is Pn. The probability of the z's exceeding 1 plus epsilon Pn is at most, whatever, some e to the negative Pn over some, epsilon squared Pn over some constant like 3 or something. And now we just have to make n sufficiently large. So n needs to be, the usual 1 over p times log 1 over delta divided by epsilon squared or something. Okay, so here we're not actually even worried that much about how big or small n is, so we can just make n big enough so that turnoff kicks in, okay, to meet this particular delta. Okay, so this is just a turnoff kind of thing, standard concentration. That one's easier. Okay. All right, so now here's this claim. Was probably at least 1 minus delta over 2. No other point has its code word within 1 plus epsilon pn. Okay. All right, so okay, so the one reason why this becomes a little bit trickier, okay, is this says no other code word, right? So, okay, so this one I only had to worry about x being close to nc of x. So I didn't have to do any union bound. And it even felt like turnoff was overkill, like we could have made this thing very small, right? Okay, but now what's a little bit tougher, this is where the transmission rate stuff comes in, okay? Because right now we have m is the ratio between m and n is fixed to 1 minus hp minus delta or something, okay? So if I make n bigger, I also make m bigger. As usual, m and n sound the same. But because the ratio is fixed, one gets bigger and so does the other, right? So we have to be careful when we do our concentration stuff because I want to take the union bound over all bit strings of length m. So every time I make n bigger by 1, I'm also doubling the number of things I'm taking the union bound over. Okay, so we're actually going to have to be more careful, and multiplicative turnoff wouldn't suffice. Okay. All right, so okay, so what we can do when we analyze this is we can fix this part. We can fix the noise of c of x and then worry about cx prime for a particular x prime. Okay. So treat that as fixed. Okay, and let's analyze what is the probability okay. All right, what can we do here?
Can we just do a simple counting argument? Like count up the number of bit strings that are within that distance from the fixed NCX. And then since each code word is random, then it's just a fractional chance that it will be in that distance out of all possible strings.
Okay, so we need to count. Okay, so I think the key point is that c of x prime is a completely random bit string. Okay, so there's some set of bit strings that's within that distance of ncx, and what are the odds of landing in it, right? So out of 2 to the n, there's like okay. So now the question then is, how many bit strings are there within 1 plus epsilon pn bits of ncx? ncx is fixed. Yeah. Okay. So this is where this entropy thing is coming in. Okay. All right. So okay. So this thing, if I were to go slowly, one step at a time, uh, this is literally counting the total number of these things divided by 2 to the n, and this is 2 to the entropy of p, at most 2 to the entropy of pn minus 1. No, it's the entropy of 1 plus epsilon p. let me do this right. I hope all my parentheses are matched. When I type in Emacs, it automatically does it for me. Okay. All right, so 2 to the entropy of 1 plus epsilon p minus 1 to the n, hopefully. Okay, that's what I have. All right, so, okay, so that was for fixed x prime, okay? Now, if I wanted to figure out the probability for all things, okay, so what I'm really interested in is what are the odds that any of them are too close, right? For some x prime, okay, how would I get this? We can do a union bound. So that will be, how many x primes are there? 2 to the m. So it'll be 2 to the m times it, which for us, because we're already doing this 2 to the stuff. So we get some expression 1 plus epsilon p minus 1 n. I did that right. Okay. All right. Okay, so this thing is at most delta over 2, if and only if, I guess taking logarithms base 2, we have m plus log of delta minus 1 or something. The divided by 2 becomes a minus 1, which I guess we can rearrange as m is less than equal to 1 minus h of 1 plus epsilon p times n minus 1 minus log of 1 over delta or something like that. Okay, now we chose okay, so we chose, why did I, okay, that's okay. So the transmission rate then is going to be m over n. Okay, so this term is essentially negligible because n will be much bigger than 1 plus log 1 over delta. Okay, so now all that's left is really to worry about this term. I don't know if it's legible because h looks like 1 plus h. Okay, all right. I want this to be like 1 minus h of p minus delta over 2 or something, if you remember what we're trying to prove. Okay, but I have an h of 1 plus epsilon p. So I want to replace h of 1 plus epsilon p with h of p minus roughly delta over 2. Yeah, so this is where we throw in the fact that we chose epsilon to be small enough that this thing is okay, something that's going to 0 very fast. All right, so that's how we get, and we chose M that so that it meets this bound. So M is small enough that it's okay. But it's really saying that M is small enough that you can actually kind of pack in all these disks. Okay. So at a high level, if you zoom back to kind of what's going on, is we had the suggestion of, oh, can you divvy up this space into kind of far apart things? And that's a little bit tricky to do. It's not clear how many of these balls you can fit into the blue. And at some level, that's what we just calculated, is that if M is exactly this much smaller than N, you can make them fit. Okay, and it's as much as you can do, basically. We have upper and lower bounds, so actually very tight. Okay. All right. Okay, so that finishes the proof. Okay, of showing that there is a good code. That was the second claim. Okay. All right. Any questions? All right. So the other part then is to show that you can't do better. Okay, because you might think that was the dumbest argument. We just chose a random code and argued that it was good, and then existentially that means there is a code that is good. But that doesn't rule out the possibility that someone actually used their brain and thought of something clever better than a completely random code, right? So what we just did is interesting insofar as we can show that you can't really do better than 1 minus entropy for the transmission rate. And in fact, the best you can do is completely random, except we don't actually know the code, we just know it exists. So that left plenty of work for the engineers. Now we have actually real constructions, and they're quite interesting. Although they have large constants and stuff, so there's other issues. Okay. All right, any ideas for how to argue that any code, I don't know if this is a guessable question because we're doing lower bounds that seem harder to think about. So I want to show that any coding scheme that claims to have transmission rate much better than what we just did couldn't possibly exist. All right, you guess and I'll review my notes. Yeah, I mean, I guess we'll prove something by contradiction. So we're going to assume first, we're going to assume there's some coding scheme that claims to have this, and then we'll find some issues with it. So I guess that counts as a proof by contradiction. I'm not even sure if there's even any cute idea to it, or it's just kind of ruthlessly going through and proving it. I think it's going to be more of that kind. All right, let's just do it. Okay, let me bring this down a little bit. All right, so let's pick some scheme where m divided by n is at least 1 minus h of p plus delta. I'm going to try to show the average error rate is at least delta. I'm going to let epsilon greater than 0. It's going to be something small, TBD. Okay. All right. Okay, so I think this is over random x, but kind of curiously, I'm going to let E be the event that the noise flips some bits, but not too many bits. So we expect the noise in general to flip p times n bits. Okay, so this is saying the number of bits it flips is at most 1 plus epsilon pn and at least 1 minus epsilon pn. Okay, so it's saying it's close to expectation. Okay, and what I want to do is I want to do it, and then yeah. Oh no, so this is all working for the fixed noise distribution where every bit is flipped with probability p. Yeah. So I should mention that in this field they work with other models too. Like, what if you just lose a bit altogether? You just skip it, right? That creates other issues. So you get n minus one bits on the other side and stuff like that. So we're just focusing on this model. Okay. So at some level though, E is something we expect to happen, and it's sort of a nice fact to have in our pocket, knowing that applying noise to X is sort of didn't change too much. It changed roughly close to expectation. Yeah? So it's going to be helpful for us to do our analysis conditional on E. So what we're going to do is we're going to say, okay, let's say the average correct rate, so 1 minus the average error rate. Okay. Okay. I'm going to say that it's at most something conditional E and not conditional in E. Okay. But I'm just going to say, so I want to show the average correct rate is smaller than like 1 minus delta, so that the average error rate is at least delta. So I want to bound this from above. Okay. And I'm going to say, okay, if E doesn't happen, I'll just say it's correct and the coding scheme did something magical. And then otherwise, I'm going to bound the probability that you do successfully decode, assuming that you don't apply too much noise to it. Okay, so E says not too much noise was applied to the message. Uh, and so when I'm trying to bound above the average correct rate, I'm going to say, okay, if there's a lot of noise, I'm just going to be generous and say, okay, you got it right. Okay, and I'm going to really focus on this part. So one reason I'm going to be able to get away with just saying, oh, if there's a lot of noise, you get it for free, is because this won't happen too often. Okay, so why won't it happen too often? Chernoff bound. Okay, so this term here, by the usual Chernoff business, is going to be at most 2e, over 3 or over 4 or whatever constant you want. Okay, and we can make n big enough and roughly make that disappear. Okay. In the rest of analysis, I now can kind of operate under the nice assumption that for this particular message, not too many bits got flipped. So it reduces some of them. Okay, good. All right, so now here comes the tricky part then. I want to analyze this term. The probability that this claimed coding scheme, okay, conditional on E. Okay. I want to be a little bit explicit about the randomness. So the randomness all along was over a random choice of X and the noise being random. Although now sort of the noise has been constrained conditionally by assuming it didn't flip too many bits. Okay. All right. Okay. All right. So how are we going to bound this? I'm going to define this set Y sub X for all X. This is the set of messages that it's a little bit inconsistent, my notation, I'm sorry. Okay, so these are the things that would get decoded. Did I write that? One sec, I have a bad typo. Okay, I think we're okay. All right, so I'll correct myself if some issue comes up. It should either be a C of x or NCX, and this I'm not 100% sure at the moment. Okay, so these are the things that will get decoded to x. That's not too far away from C of x. Possibly it should be NC of x. I'm not 100% sure at the moment. We'll find out in the next 3 minutes, I promise. Okay? Um, okay, so now let's write the probability of the thing up above, NC of x, equal to x, given E. Okay, is equal to, let's see why I wrote this, 1 over 2 to the m. Okay, so you're choosing a random x. Okay, so I'm summing over all possible x's, but there's 2 to the m of them. That's why there's a 1 over 2 to the m. And I'm summing over all of these points y that would get decoded from it. The probability that NCX is equal to y. Okay, so this makes sense. So y is everything that for particular x, y sub x is all the points that will get decoded to x, but is also close to the code word of x. Okay, fine. Okay, and now what's one of these terms? The probability that NC of x is equal to y. Okay, is okay, so y differs in at least 1 minus epsilon p n bits from C of x. Okay. So on one hand, it's bounded above by, these are the odds of flipping exactly those bits. Okay. And if you start now putting everything into the log, so if I wrote 2, 1 minus epsilon p n log of p, plus 1 minus epsilon pn log of 1 minus p, something like this. Okay. And if you're impatient to leave, so you believe this next step I did correctly, okay, you should get 2 to the negative entropy pn times 1 minus p over p epsilon pn. Okay. Just yell at me if you think I'm wrong. Or yell at me if you know I'm wrong, but keep it to yourself if you suspect I'm wrong. Okay? I'm pretty sure it's right. We're just in a rush. So if I go back to this term up here, okay, and I plug this in like that, okay, and everything's going to work out really nicely, I hope. So this is at most 1 over 2 to the m. Oh, no, we already did that. 2 to the n minus m, 1 minus p over p epsilon Pn. Okay, I realize we're just doing calculations at this point. Okay. But the claim was this value of m was bigger than 1 minus hp n plus delta n. Okay. So you get 2 to the minus delta n, 1 minus p over p epsilon Pn. Okay. So this is, finally, we're almost done, 2 to the epsilon log of 1 minus p over p minus delta to the n. Okay, so whatever, you do all these calculations, you come back through. Finally, you can make epsilon as small as you want. Okay, and so you end up getting something like 2 to the negative delta n, which will get really, really small. This is the average correctness rate, so you can drive this thing down to 0. Okay, so at some level, what it's kind of telling you is that this entropy in counting sets with 2 to the HP is really tight. And if you cheat and claim a transmission rate that's kind of above what some of these bounds give you, then you cheat too much and we can drive some things down to 0 and prove you must be lying. That makes some high level sense. And you'd have to probably just double check the calculations afterwards to convince yourself. It is what it is. Okay, but the impact is very important. I guess this is, again, I would consider second proof maybe more so than being an interesting proof, an interesting consequence, right? We did the dirty work that we had to do. We did the calculations somewhat quickly, but it gives you the upper and lower bound and kind of establishes a universal law of coding theory. And we're done and we're late. Sorry about that. Okay, thank you.